Okay, so here we're just going to go through some physics topics in paper 2. So this is a diagram of a wave. Let me just go through the terminologies or some terms. So you've got amplitude, you have crest, you have peak, you have trough, you have equilibrium position. So let's have a look at this one first. So here we have a wave and a half and a bit. Can you see where that one wave ends? So this wave ends here, right? So here we have one wave. So here we have one wave, and it ends at 20. So the time it takes for one wave in this case is 20 seconds. We're assuming that this unit is in seconds. So if it was minutes, then it would be 20 minutes. Let's assume that this one's in seconds. So the period is the time it takes for one wave, and in this case is 20 seconds. This equation for wave, so v equals f lambda. So speed is frequency times wavelength. So if the speed was 10 meters per second and the frequency was 2 hertz, the wavelength was 5 meters. You have 10 meters per second equals 2 hertz times 5 meters. Right, what else? So at the top we have the crest, you've got the peak, equilibrium position is in the middle, right? So in the middle, this is the equilibrium position. Here is the crest or the peak. Here you have the trough. The amplitude is from here to here, right? That's the amplitude, or it could be from here to here. So that is the amplitude. Here is also the amplitude. Wavelength. Wavelength is the distance from one crest to the next crest, or it could even be from here to here. So it is really from one point on the wave to the next point on the wave. So that is one wavelength. So one wavelength here could be from here to here, right? That is one wavelength. Okay, that is one wavelength. Now let's look at this. This is a ripple tank. If we zoom in, so here we have the peak to peak is the wavelength. So if you have a look on the right hand side, the wavelength has gone down compared to the one on the left. So the wavelength is from peak to peak, and the period, the symbol for period is T, the symbol for frequency is F. So 1 over the frequency is the period. So how will you calculate the wavelength? So what you could do is that you could count the number of peaks. In this case, you have, let's just say 6. All right, that's 1, 2, 3, 4, 5, 6. Let's just say 7. Let's just say 7 from here. Right, so here we got 7. So you count the number of peaks. In this case, you have 7 peaks. Let me see, 1, 2, 3, 4, 5, 6, 7, and you divide by the time it takes, right? So you count the number of peaks, you time, and then to work out the frequency, you do the number of peaks divided by time taken, because frequency is how many waves per second. Okay, the period is the time, is how long it takes for one wave. So well, I'm just using this example here. If you have 6 peaks in 12 seconds, then your frequency is 6 divided by 12. But you do the number of peaks divided by the number of seconds, so you have 0.5 waves per second. So your frequency is 0.5 hertz, is your F. Your period is 1 over F. So 1 over 0.5 is 2. So 2 seconds will be your period. Right, transverse waves, they oscillate 90 degrees to the energy transfer. Longitudinal is oscillations parallel to the energy transfer. While sound moves faster in warm air, it doesn't travel as fast as it does in colder temperatures. So because it's to do with high kinetic energy, so when it's warm, the kinetic energy is high, so it travels faster. But because colder temperatures is more dense, but it is slower, it will travel further, right? It will travel far. So although cool air, it is slower, warmer air is faster, but in colder temperatures, it is further, it travels more further. So temperature isn't the only thing that affects the speed of the sound. For instance, humidity also has an impact by making air less dense. Low humidity helps sound moves faster, but not further. Right, so here you got 6 different types of wave properties. So they can reflect, they can be transmitted through the object, it can be refracted, absorbed, diffract, and scattering. So reflection is when incident light, incoming light, hits an object and bounces off. Very smooth surfaces such as mirrors reflect almost all incident light. Absorption occurs when photons from incoming light hit atoms and cause them to vibrate. So they have absorb, right? So it causes it to vibrate, it absorbs. So the more an object's molecules move and vibrate, the hotter it becomes. The heat is then emitted from the object as thermal energy. Diffraction is the bending and spreading of waves around an obstacle. It is most pronounced when a light wave strikes an object with a size comparable to its own wavelength. So if the size is 3 centimeters and the wavelength is also 3 centimeters, you will see lots of diffraction. Scattering occurs when light bounces off an object in a variety of directions. The amount of scattering that takes place depends on the wavelength of light and the size and structure of the object. Refraction is when light waves change direction. So when it changes direction as it passes from one medium to another, light travels slower in air than in a vacuum and even slower in water. As light travels in a different medium, the change in speed bends the light. So the change in speed bends the light. Different wavelengths of light are slowed at different rates, which causes them to bend at different angles. Short wavelengths are slowed more sharply upon entering glass from air than are long wavelengths. For example, red light has the longest wavelength and is bent the least. So if you remember that red will be bending the least, and violet is the short wavelength and it is bent the most. So bent the most for violet. So violet light travels more slowly through glass than does any other color. Violet travels the slowest, so it is on the bottom, and red travels the fastest, so it is the top. This is because, well, this is also called this leads to the index of refraction. Okay, so let's explain a bit more. So using V equals F lambda, right? Using the equation V equals F lambda, when lambda goes down, V goes down. But because red is longer, for red, the speed is higher than violet. So the violet is the shortest, and so the speed is the lowest, is the biggest change using the equation. Right, so again, blue or violet bends the most, and red bends the least. Right, the deeper the water, the faster the waves travel. So the waves will refract when they enter deeper or shallower water at an angle. So the deeper the water, the faster the waves travel. The deeper the water, the faster the waves travel. Now, if you look at this, the particles move up and down, although they do move sideways, but they move more up and down, right? So the water molecules move up and down for a water wave, but the energy transfer is going this way, right? So the water particles is moving up and down, but the energy transfer is moving from left to right. The visible spectrum is the segment of the electromagnetic spectrum that the human eye can see, right? That's why we call visible. That's why we call visible light. This range of wavelengths is called visible light, and it is roughly between 400 nanometers to 700 nanometers, right? So what is the electromagnetic wave? Electromagnetic wave is a wave where there's electric field and magnetic field components, and this is in the electromagnetic spectrum, right? Right, factors affecting temperature. Now, the temperature of a body is linked to the balance between the amount of radiation absorbed and emitted. So the more, okay, so if the rate of absorption is bigger than the rate of emission, so when there is more in than out, the temperature goes up. Temperature goes up. When it is the same, it is constant. But when the rate of absorption is now less than emission, the temperature goes down. So if you look at this, if an object absorbs more radiation, it becomes hotter than it is emitting less. And when it is emitting more than absorbing, the temperature is colder. Right. Radio waves are used for communication, such as broadcasting, television, and radio communications and satellite transmissions. Radio waves are transmitted easily through the air. They do not cause damage if absorbed by the body, and they can be reflected to change their direction. These properties make them ideal for communications. Radio waves can be produced by oscillations in electrical circuits. When radio waves are absorbed by a conductor, they create an alternating current. This electrical current has the same frequency as the radio waves. Information is coded into the wave before transmission, which can then be decoded when the wave is received. Television and radio systems use this principle to broadcast information. Infrared light has frequencies which are absorbed by some chemical bonds. The internal energy of the bonds increases when they absorb infrared light, which causes heating. So let's just think of a bond, right? If you have a chemical bond, this is a bond, and it absorbs infrared light, which causes heating, right? So the temperature goes up. Remember, when something is absorbed, this is radiation, the temperature will go up. So which causes heating. This makes infrared light useful for electrical heaters and for cooking food. All objects emit infrared light, right? If you have an object, they will emit light. Objects will emit light. The human eye can't see this light, but infrared cameras can. This thermal imaging is useful for detecting people in the dark. Ionizing radiation. Ultraviolet waves, X-rays, and gamma rays are types of ionizing radiation. So UV, X-rays, and gamma rays, ionizing radiation, they can add or remove electrons from molecules, hence the word ionizing, right? Ionizing, they can add or remove electrons, producing electrically charged ions. Ionization can cause hazards, can have hazardous effects on the body. So UV waves can cause skin to age prematurely and increase the risk of skin cancer. X-rays and gamma rays can cause mutation of genes, which can lead to cancer. This is refraction. So when light goes into a different material, it will refract. The change in speed causes it to refract. Remember that the frequency stays the same. It's the same, right? The frequency stays the same. Okay, so here the focus is in front of the convex lens. So this is convex. The focus is here, and the image is upside down but real. This is the same, right? Remember, if this is the same, when the absorption is the same as the emission, the temperature stays constant. Okay, radiation. If you have too many protons, it will be unstable. Unstable. This one is stable. And so here, unstable will give off radiation. So here, an isotope. An isotope have the same number of protons, right, 6, but different number of neutrons. It's the same element because it has the same number of protons. This is the alpha decay, beta decay. For GCSE, you just need to know beta minus. You can get beta plus, which is the positron. But for GCSE, you just need to know the beta minus. So this is the symbol for the beta decay, 0 minus 1. For alpha, it is the helium nucleus. And it has a charge of 2 plus. So if you have, is it radium? Or is it, yes, radium? I think it's radium. It doesn't matter what element it is. The point is that it loses 4. The proton loses 2. And you have an alpha particle here. Right, this is the nuclear equation. So it loses 4. So if you take away 4, that becomes 224. And here it loses 2. And it leaves with a alpha particle. Similarly here, if you have beta minus, remember this is minus. So if you got 6, you have to add 1. So So here you have to add 1 because of the conservation of charge. The thing is, because you have too many, here you have too many neutrons. So if you have too many neutrons, um, the thing is, if you have too many neutrons, the neutron becomes a proton, and it also emits an electron. So this is the conservation of charge. That's why you have 7 here. So because you have a -1, this has to be 7 if this was carbon 6. Gamma radiation, this is just excited. This is just excited. There is no loss of mass, so it's the same because it's 0, 0 for gamma. Right, imagine these are energy levels. I know these aren't perfectly circles, but imagine they are in orbits, right? If they're in orbits, imagine you have an electron. It absorbs a photon, right? It absorbs a photon, and it goes to a higher energy level. It goes to a higher energy level, right? And then it is now excited. It is excited. But because it is excited, it may not stay there for very long. So what happens? It goes back down in energy level, and it will emit a photon. It will emit a photon or radiation, right? So it will emit radiation, and yeah, it will fall back down again. So different energy levels will give off different frequencies. Different energies will give off different frequencies of radiation. Right, radioactivity. What is half-life? Imagine you got 400, and imagine you got 400 atoms. This was 10. Let's start again. The half-life of this substance is 10 days. So let's just start off with let's start off with let's just start off with 800 atoms. After 10 days, you've got 400 atoms. After 20 days, you've got 200 atoms. After 30 days, you've got 100 atoms. After 40 days, you've got 50 atoms. So the atoms gets half, yeah, gets half every time. So also, the activity is halved, right? So let's just say that the half-life is 2 days. Every 2 days, the activity is halved. So 40 becomes 20 after 2 days. 20 becomes 10 after 2 days, right? So you can do 20 and 10. Let's just say you got 20 and 10. You go across, you get from 4 to 6 is 2 days. 4 to 6 is 2 days. That's the half-life, and the activity has halved. Again, from 40 to 20 is halved, but also it's 2 days again. So the half-life, right, is the time it takes for the nuclei to get halved or the activity to be halved. Okay, so the time it takes for number of nuclei to halve or the activity to halve. Let's look at this graph here. So the blue line is the original nuclei. The red line is the new nuclei, right? So the blue line is the original nuclei. The red line is the daughter nuclei. The original nuclei decays into the new or daughter nuclei. So the red line is the new nuclei. So it's the one that's been decayed into. The blue line is the original. So the half-life of a radioactive isotope is the time it takes for one half of the radioactive isotope to decay. One half to decay. The half-life of a specific radioactive isotope is the same, is constant. It is unaffected by conditions, and it is independent of the initial amount of that isotope. Right, what stops alpha, beta, and gamma? So normally paper can stop alpha, aluminium will stop beta, lead and meters of concrete will stop gamma. Right, so alpha can be stopped by paper or skin. The penetration in the air is about 5 centimeters. Why is it high ionizing? Beta can be stopped by aluminium. In the air, it's about maybe 1 meter, and it has low ionizing power. For gamma, in the air, it can be attenuated, meaning it will be reduced. The energy will be reduced about 1 kilometer. It can be reduced by lead or concrete, meters of concrete. So Why was it ionizing for alpha? Because the charge of alpha is 2 plus. Remember, you got 2 protons in the helium nucleus, right? You got 2 protons, which is 2 plus. The beta is the electron. The thing is, yeah, let's just do GCSE, right? So the beta is the electron, and the gamma, there is no charge. So in terms of the ionizing particle power, the alpha is 2 plus, beta is -1, and gamma is a 0. Beta particles are more penetrating than alpha particles because they are because they have a small mass, right? The beta particles have a smaller mass, and they won't get stopped easily compared to alpha, but are less damaging to living tissue and DNA because the ionizations they produce are more widely spaced. They travel further in the air than alpha, but it can be stopped by clothing or a thin layer of aluminium. Some beta particles are capable of penetrating the skin and causing damage such as skin burns. However, as with alpha emitters, beta emitters are most hazardous when they are inhaled or swallowed. Right, a radioactive source producing beta radiation is used to control the thickness in the manufacturing industry. In this example, the thickness of aluminium foil is controlled by measuring the amount of beta radiation that passes through it. So if you look at this, this is a device in industry. You would put a beta emitter and this aluminium foil, this is a detector. What happens? If the foil is too thick, it absorbs more beta particles. The detector receives less beta particles and then sends a signal to the rollers to increase the force on the foil, making it thinner. If the foil is too thin, it absorbs less beta particles. The detector receives more beta particles and then sends a signal to the rollers to decrease the force on the foil, making it thicker. So, irradiation and contamination, what's the difference? So, contamination is when it's in you or on you. Irradiation is usually through you, and you can eliminate the source. So, let's describe it. Object is exposed to radiation but does not become radioactive. This is for irradiation. The source, the danger from radiation outside the object. Prevention, you can shield, such as lead clothing. Causes, causes by a presence of a radioactive sources outside the body. But look at contamination now. Contamination. So the object becomes radioactive and emits radiation. The danger from radiation emitted within the object, prevented by safe handling or sources and airtight safety clothing, and it is either inhaled or ingested. So now it is on you. Okay. What do you use? What's the application? So you can use tracers. So imagine you have a tracer, right? You have a tracer, it is going through the pipes. As it's traveling through the pipes, if there's a leak, there'll be a high count rate because let's just say it's gamma, right? And gamma is very penetrating. Remember, it can be very penetrating. So if there's higher radioactive counts per second, it means there's a leak here, and it needs to be penetrating. If the source is going this way, the detector, right? Okay, another use. You can use it for further medical imaging. So you can detect tumors using the flow of radioactive material. And here there's a scan. The computer does it for you. Let's just say it emits gamma radiation again. Gamma radiation. You have a detector, and it measures the amount of detects the amount of gamma radiation. Right, a gamma knife. A gamma knife can be used to kill cancerous tumors deep inside the body. The beams are aimed at the tumor from different directions to maximize the dose on the tumor, but to minimize the dose on the surrounding tissue. That is why it has to be focused it has to be focused the target. The technique can damage healthy tissue, so careful calculations must be done to establish the best dose, enough to kill the tumor, but not to damage the healthy tissue. Okay, so advantages and disadvantages of irradiation. So sterilization can be done without high temperatures. It can be used to kill bacteria on things that would melt. disadvantages. It may not kill all bacteria on an object. It can be very harmful. Standing in an environment where objects can be treated by irradiation could expose people's cells to damage and mutation. Right, this is fission. Fission is when you have a large nucleus, right? You have a large nucleus and it splits into smaller nuclei and with neutrons, right? So you have either 2 or 3 neutrons. So the neutron hits the uranium nucleus, it splits into smaller nuclei and these neutrons, and what does it release? It releases energy. Nuclear fusion. Nuclear fusion is when you have 2 nuclei combining to make a larger nuclei, right? So this is combining, and it also releases energy. Right, so fusion is when you're joining together smaller nuclei into larger ones. So for example, the nuclei will be small nuclei like hydrogen. It happens in stars. It produces a lot of energy and it produces larger nuclei. But it does require high temperatures and high pressure. Because if you have 2 protons together, remember they are charged, they will repel. So you need to overcome the repulsion. Fission. Fission is when you have a large nuclei and it splits into smaller nuclei. So such as uranium, nuclear reactors. Also produces lots of energy. The nuclei, daughter nuclei, and it also releases 2 or 3 neutrons. But you also need high temperatures and neutrons to induce fission. Right, electromagnetic spectrum. Ionizing radiation is when it's above ultraviolet, right? And below that is non-ionizing. Right, so this is to do with kinetic energy, potential energy. So let's just say you kick a ball with high kinetic energy, but there's low potential energy because the height is low. Here, high potential energy because the height is high. But why is it little kinetic energy? Because the speed is now lower. Right, the speed is now lower, and then it falls back down again, falls back down again. There's higher kinetic energy because now it speeds up, and the height is low. The height is low. So these are some equations. Force times distance is work done, and it is energy. Okay, so remember that force times distance is work done, energy. If you were to convert energy, let's just say converting kinetic energy into potential energy, you can use half mv squared equals mgh, and then solve. Power equals current times voltage. So P equals IV. You also know that energy is power times time. So energy is power times time. But because you know that P is IV, you can say that energy is ITV. This is for electrical circuits. Efficiency is useful energy divided by input energy, right? How do you increase efficiency? You would reduce friction. You could lubricate to reduce friction. You can use insulation. That will reduce energy loss. So for example, for houses, you would have more insulation to reduce heat loss. A material with a high thermal conductivity transfers energy more quickly. A material with a low thermal conductivity transfers energy slowly. So have a look at these. Just have a look at these methods for increasing insulation, reducing energy loss. These are some examples of speeds. Just have a look at some of these speeds for everyday usage. So these are typical speeds that you do need to memorize or recognize. So this is stopping distance. Reaction distance equals reaction time times the speed of the car. This is for braking because there is an acceleration involved. Stopping equals thinking plus braking. This is the life cycle of a star. First, you start off with a protostar, and it goes to a main sequence star, and it goes off to two different branches. If the mass is low, let's just say the same size as our sun, it becomes a red giant, then becomes a white dwarf, and then it becomes a black dwarf. But if the mass is much bigger than the sun, it will be a red supergiant, supernova, black hole, or neutron star. So, life cycle. Stars begin as a cloud of dust and gas, are brought together by gravity. This cloud is called a nebula. Gravity causes the dust cloud to become more hot, more dense. The mass increases. It is now a protostar. Eventually, the temperature and pressure becomes very high to undergo fusion, and then hydrogen fuses to make helium. The fusion keeps the reaction going. Now we have a star. The protostar becomes a main sequence star. In main sequence stars, the outward pressure caused by nuclear fusion is balanced by the gravitational forces caused by the mass of the star. Stars usually remain in the main sequence for several billion years. As the star leaves the main sequence, when the hydrogen runs out, what happens next? Well, there are two situations. So, if the star is the size of our sun or less, it becomes unstable, expands, it becomes a red giant. The star then removes or ejects its outer layers and it becomes a white dwarf, which is very small, hot core of the star. Finally, the white dwarf cools into a black dwarf. If it is much bigger than our sun, it becomes a red supergiant. It will continue expanding, there's more fusion, and up to iron, it will still carry on with fusion all the way up to iron. The supergiant eventually becomes so big, there's gravitational collapse, and it becomes a supernova. This is a massive implosion and then explosion where fusion occurs and heavier elements are made. So the explosion ejects the outer layers of the star into space. What you're left with is either a neutron star or a black hole. A black hole is an extremely dense point in space and it has a strong gravitational field, not even light can escape. The neutron star is very dense where everything is just neutrons. Right, redshift. Redshift, if something is redshifted, it means it is moving away from us. So astronomers see redshift in virtually all galaxies. It is the result of the space between the Earth and the galaxies expanding. This expansion has the effect of increasing the wavelength of the light from these galaxies, shifting towards the red end of the spectrum. The more redshift there is, the faster the galaxy is moving. So, the prediction from the Big Bang. More distant galaxies are moving away faster. We see more redshift. Yes, it supports the Big Bang. Initial Big Bang heat should be now thinly spread across the universe. So because of the cosmic microwave background radiation, CMBR, we see microwave because before it was gamma rays, it's been stretched into microwaves and the temperature is about 3 Kelvin. So if you look at the redshift, can you see that the very distant galaxies, the arrows are now going towards the red end? If you look at the spectrum laboratory reference, you can see that the lines are now redshifted, meaning it is now longer. The wavelength is now shifted to the right. So Hubble eventually determined that the velocity at which these galaxies are receding was proportional to how far away they were. The further away the galaxies, the higher their redshift was. So here, moving away is redshifted, the wavelength gets longer or the frequency is lower. If it's moving towards you, it is blue shifted. The wavelength is shorter, frequency is higher. So Hubble's law, where the further away the galaxy is, the faster it is moving away. So all galaxies appear to be receding from our location in space. This is not because the location of the Milky Way is special. Instead, it is realized that this is because the entire universe is expanding. Space-time is expanding, stretching.